Hello, in this video I'm going to solve the following problem for you. State that whether the following integral converges or diverges and justify your claim. Integral from 0 to infinity dx over square root of x ln of x. That would be a good idea if you pause the video at this point and give it a try yourself. If you understand the problem correctly, the answer will be the integral diverges to infinity. Okay, now let us do this. First of all, you see that because of existence of this infinity, so the integration interval is unbounded, so this is an improper integral of the first kind. But because there is no number within this interval that makes the function f of x. I mean, if, for example, if x is a number greater than 2, a finite number, so let me write it a, then the limit of f of x when x goes even greater than or equal to, if x goes to a from the right hand side, is always finite. Yes, this is exactly equal to 1 over square root of a ln of a. So this is an integral, improper integral of the first kind, but not improper integral of the second kind. Okay, one way to do it is start working with this integral or do some substitution. Yeah. So for example, if you say let us take a square root of x to be capital X, then what happens if I differentiate both sides? This becomes dx over 2 square root of x equals to dx. And because dx over square root of x is something I need, I multiply everything by 2. Then I will get this expression. And then because little x is supposed to go from 2 to infinity, this would then imply that capital X goes from square root of 2 to infinity. Yes? If little x is 2, capital X becomes square root of 2, and the limit of this when x goes to infinity again becomes infinity. And then of course from here I know that little x is also capital X squared. So if I call this integral I, we expect that this integral can also be expressed in this form. Instead of 2 to infinity, it becomes square root of 2 to infinity. And instead of dx over square root of x, I write 2 dx. And then instead of ln of little x, I write ln of capital X squared. But this 2 will go behind the log here because x is positive within this interval, so no problems, and that 2 will cancel that 2. So finally I will end up with a little bit simpler integral. And I have to be worried about logarithmic function here. I don't have a combination of this function and logarithmic function. Okay, so let us deal with that one. My claim is that if I am working on this interval, in other words, if capital X is greater than or equal to square root of 2, I want to show that ln of x is less than or equal to x. And by the way, this is understandable because ln of x will be dominated by any polynomial or any power, positive power of x. This is a famous limit, famous information that you should have in this course. Okay, so let us first try to see that this is correct or not. As usual, for these kinds of inequalities, I define a function, ln of x minus x, and I differentiate it with respect to capital X. The derivative of that is just simply 1 over x minus 1, and if I take the common denominator, this becomes that. Okay, but x is greater than or equal to square root of 2, so this is positive, but this one becomes negative. Yes, so this is indeed a strictly negative number, so this means that g is actually decreasing. Okay, I know that x is greater than or equal square root of 2, and we just realized that g is decreasing. So what can I conclude from here? I can conclude that g of capital X is less than or equal to g of the square root of 2. But g of capital X is ln of x minus x, as I defined it there. G of the square root of 2, it means every x should be replaced by square root of 2. So this becomes less than or equal to ln of the square root of 2 minus the square root of 2. But let me move x to the other side. So this becomes ln of x less than or equal to x plus, I would write, I want to understand what type of number is this. Is it positive or negative? So instead of square root of 2, I write 2 to the power of 1/2. 1/2 goes to the back of the log. So this becomes 1 over 2 ln of 2 minus the square root of 2. Let me put it in a pair of brackets. But this is easily seen that this number is negative, yes? Why? Because ln of 2 is less than e, the Euler number. So ln of 2 is less than 1, yes? So if it is less than 1, when you divide it by 2, it becomes less than half. A number less than half minus the square root of 2 definitely is negative. And if ln of x is less than or equal to x plus a negative number, definitely it is also strictly smaller than x itself. Okay, now I know that ln of x, actually I know even better, so I can take this off. So ln of x is strictly less than x, but are these numbers positive? X is definitely positive because it is greater than a square root of 2. Ln of x is also positive because if x is greater than or equal to square root of 2, it is definitely greater than 1. So ln of x becomes greater than ln of 0, which is ln of 1, which is 0. So ln of x is also positive. So I don't have any problems to take the reciprocal and swap the sign. So it becomes 1 over ln of x is greater than 1 over x. Yes? If a number, the denominator of this number is less than the denominator of this number and they are positive, so it means the fraction itself is greater than this fraction. Okay, but then integral from square root of 2 to infinity 1 over x dx, this is one of those simple integrals. So this integral diverges, yes? If you have forgotten the theorem, you can do it yourself. So for example, you can write a limit integral from square root of 2 to some number r, but you have to send r to infinity, 1 over x dx. But this is just very famous, 1 over x, the primitive function is ln of absolute value of x. So if I continue here, this becomes the limit, r goes to infinity, and then I have ln of absolute value of x. X goes from square root of 2 to r, and then r goes to infinity. So this is simply limit of ln of r. I don't need absolute value because this is positive. The square root of 2 is also positive. And r goes to infinity. This is a finite number. Ln of infinity becomes infinity, so it becomes infinite. So what does it mean? It means that this integral diverges. Our original integral here, the integrand of that on the integration limit, on the integration interval is greater than this integrand, and they're all positive. And if the bigger one, if the smaller one diverges to infinity, so does the bigger one. Okay, so this means that I realize that yes, this integral actually diverges to infinity. So this is one way of doing it. Another way might be we can start tackling the problem from the very beginning by understanding that if I ask you what is the limit of the square root of x over ln of x when x goes to infinity, the answer is infinity, yes? This is very famous. Every positive power of x will dominate ln of x if x goes to infinity. And of course you can use Hopital's rule to understand that, because the limit of this expression can be written as x to the power of 1/2 ln of x when x goes to infinity, and this is infinity over infinity, so Hopital's rule is applicable. The derivative of this one becomes 1 over 2 square root of x. So let me calculate the derivative of the numerator and the derivative of the denominator, and x goes to infinity, so x goes up, x goes to infinity, but this can also be written as a square root of x over 2 when x goes to infinity, so of course it becomes infinity. Anyway, this is a very famous result. You don't even need to prove it. Any positive power of x will dominate logarithmic function when x goes to infinity. But what is the meaning of this? Okay, so if you say the limit of a function f of x is equal to infinity when x approaches infinity, by the definition of the limit, it means that for all positive number n, for all positive number m, there exists another positive number n, so that when x is greater than that n, this would imply that f of x is greater than m. That is the definition of the limit when x approaches infinity becomes infinity. So in this case, I know that the limit of a square root of x, ln of x, x goes to infinity, becomes infinity. So it means for every positive number, including, for example, number 1, I can find an n in greater than 0 such that if x is greater than n, then my function square root of x over ln of x becomes greater than 1. I have chosen m to be 1 because if the limit is infinity, this statement should be true no matter what you choose for the positive m. Here I decided to choose 1 for it. Okay, of course I can also do better. Yes, I can claim that this n that I am looking for is also greater than 2. Because if the n that exists is greater than 2, and we know that, we are done. If n is less than 2, and this will work, of course I can choose another n which is greater than 2, and still this works. So here I can say that this n can also be greater than 2. Okay, but what does this mean? This means that if I am beyond that number, then square root of x is greater than ln of x. I multiply everything by square root of x. This means x is greater than square root of x ln of x. So I multiplied both sides by square root of x because x is positive. Okay, so then it means what? Then it means that 1 over x is less than 1 over square root of x ln of x, or in other words, 1 over the square root of x ln of x is greater than 1 over x. Okay, but this inequality holds if x is greater than that n. So this, but there is no guarantee. So I want to use that inequality. So if I go back to the original integral, so I have to break my integral from 2 to infinity, dx over square root of x ln of x. I break it into 2 parts, one from 2 to that n, which I don't know what that n is, but I know that that n exists. So and it is greater than 2. So I go from 2 to n, dx square root of x ln of x plus the integral from n to infinity dx square root of x ln of x. In principle, for the time being, I don't need to put plus. I need to investigate about these two integrals separately. I don't have any problems here. Why? Because the function involved is continuous on this integral, and if the function is continuous, it is also integrable. It means that the value of this definite integral is a finite number. So this is a finite number, and for this one, I realize that on the interval when x is greater than n, which is exactly this interval, my function is greater than 1 over x. But then the integral from n to infinity, 1 over x dx, diverges to infinity. So does this integral. Okay, so then it means that because this part is infinite, this part is finite, the original integral diverges to infinity. So that's also one alternative way to look at the problem. Okay, so I intentionally wanted you to use these tricks. So if you know information about the limits of the function, you can find very useful inequalities without having to find the exact form of the inequality, because that is not the goal. You might spend a lot of time and find the optimal inequality, but finding the optimal inequality is not the target in these problems. So as far as you can find an inequality within some interval that you know it's working, that's enough. But of course, you can always find probably what we can say optimal inequalities. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.